So welcome everybody to the seminar. Today I welcome Sergio. So most of you know him. Sergio got his PhD in 25 at the Instituto de Astrofísica de Canarias. I hope my pronunciation is not worse than expected. Under the supervision of Artemio Herrero, correct me if I'm wrong, Sergio. Yeah. And after his PhD, he did a first postdoc of 1 year at the IACOB before moving for 1 year at Geneva and after that to Paris-Meudon, right? Mm-hmm. And after this trip abroad, he come back to Tenerife for 2 different postdocs, and now he's a permanent researcher at the IACOB. And since 2008, he's the PI of the IACOB project, and I think he will talk about it later. And now he's the PI of the IAC research group on physical properties and evolution of massive star. And I personally know him for about 10 years now, and it's always a pleasure to talk with him, both for science and life in general. So it's I'm very happy to that you are with us today and present the latest results about the IACOB project. So the floor is yours, Sergio.
Okay, thank you very much, Laurent. I want to say thanks for this invitation, and especially this surprise that you have these 2 extra sessions that I think are really important. No? First, that we will be able to discuss more in detail with a coffee, and then this meeting with the student. I think this is very, very interesting. So I will try to put something similar here at the IC. Okay, so this talk was supposed to be before Christmas from Mercator. This was going to be a surprise because I had an observing run. But then I had a lot of evaluations from a postdoc here, so I told Logan to postpone it. So on the other side, it's great because I have more results to show. So, okay, so you can see my screen here. Yeah, I assume yes. Okay, so I will be telling about the IACOB project, and the title I've decided for this talk is a massive empirical approach to unveil the mysteries of galactic high mass stars. So this is kind of playing a bit with the words. Massive in terms of massive stars, but also massive because it's, as you will see, a large number of stars to be studied, no? And then we are talking about stars in the galaxy. So this is kind of complementary to what we've been doing in BFTS with the Tarantula Nebula. So I want to say thanks and to show these pictures, these photos of the people, my collaborators who has contributed to the things that I will be showing you in this talk, but there are many others there. So maybe in another talk you will see different faces. Okay, so let's start here. I'm sure all of you recognize the Orion constellation, Orion the Hunter, in this very nice image. Just in case for those that are a bit lost, that probably anyone. So this is Orion. I'm sure most of you know the stars in the brightest stars in the constellation, and maybe some of you know even the Greek or Latin names. And probably some of you know also that all these brightest stars are high mass stars. Most of them are O P type, and then we have also Betelgeuse, that is a red supergiant, but all of them are massive stars. So it's with the spectroscopy and then the analysis, we can put these stars in a HR diagram or the spectroscopic HR diagram, and you can see how these stars are distributed in the HR diagram. So they have different masses and different evolutionary status, but they are not connected because this is not a cluster. This is just by chance that these stars are in the same position of the sky. They are in the same, more or less the same place in the galaxy, but they are not connected. But you see how investigating bright stars, you can begin to learn about the physical properties and the evolution of massive stars. So for me, the Orion constellation and the stars in Orion have been very special because I've done many things with them. And this allows me to go to the main topic of this talk, that is the massive star domain. So here I introduce the diagram that was prepared by Norberto Castro already in 2014. He compiled data with, data from the literature with parameters obtained spectroscopically. So it was around 600 stars. And then he could create this density map here. So where you have stars in this figure is phases in which the stars evolve not so quickly. So it's a kind of, it's giving you some clues about the evolution of massive stars. No? So this is about physics, but then we can also talk about morphology. And this is very important to take into account that the connection between the physics and the morphology sometimes is not so easy. So for example, sometimes we confuse we say that the O stars are main sequence stars, but then the O supergiants are post-main sequence stars, while actually this is not necessarily true. So depending on the models, these stars, or we are still not sure if these are main sequence stars or no, and the same with the B supergiants. So we have to be very careful with the connection between all these names that came from a morphological description of the spectra we see, and then the actual physical properties of those. So I will be talking about massive stars, and I think in this audience I don't need to explain very much about the importance of massive stars, and so I'm going to jump this one, but basically just to remember that they are not only cosmic engines through space and time, so from the solar neighborhood to the early universe, but also, as Rolf Kudryski and Joachim Puls say in his review in 2000, they can be considered as gifts of nature for the study of the universe, because they have a lot of features that tell us a lot about not only the stars themselves, but also important physics to be considered in stellar astrophysics, and about the galaxies where they are located. Here we have the OB stars. So OB stars are a very important evolutionary phase of massive stars, because they are connected probably with main sequence, most of them with main sequence stars. And there are many, and it's kind of the starting point of the evolution of massive stars. So the study of OB type stars is very important. And here I summarize the main properties of these stars that I'm not going to say in detail, but basically just to say that, as many of you know, these properties that make this star very extreme makes the modeling and the study of this star is complex. And if we also consider that the number of massive stars in comparison with the late type stars is much smaller, then every star that we discover and we analyze is like a really a treasure, no? So having more and more data for massive stars is very important for many topics. And this is the idea of the IACOB project. So in 2008, more or less, I started what I decided to call IACOB. When Joachim Puls told me you should put a name to your project, so I decided IACOB, and I think it's obvious why it's called IACOB. And the idea here is to try to get as many empirical information as possible for a large sample of galactic massive stars, with the idea that all this observation, analyzed properly, could be used as an anchor point for our theories of stellar atmospheres, winds, interiors, and evolution. So the idea is to do this empirical characterization of several thousand. We are going, as you will see in this talk, we will be able hopefully in the next 5 years to reach 10,000 stars or more. And then we start from the observation, and then we determine the stellar and wind parameters. We obtain the surface abundances. We try to identify and study empirically binary multiple systems, and we also take into account other things, important things like stellar variability. So the idea is to provide like a global overview of all the empirical properties of a large sample of massive stars. So why is it so important to consider so many stars? Well, here I put like the tracks from the bond group, just non-rotating tracks. And you see that in this case, if we have the properties, temperature and gravity, for example, or luminosity of one star, and you put the star in this diagram, then you can obtain the mass and the age. But then, as you know, in massive stars, this is not so simple. So first, we have the evolution of massive stars also depends on rotation and stellar winds. And we know that the projected rotational velocity of mass stars can reach up to 600 kilometers per second. So, and this is affecting a lot the internal structure of the star, and also how the products generated in the interior are traveling to the surface, and also how the wind is spelled and everything. No? Obviously, we have also metallicity, and stellar winds is the way the stars are losing mass, and this is also affecting the evolution. No? Also, we have that, you know, about the blue loops. So when we, well, the first thing is that all these extra parameters is kind of mixing all the tracks. So then it's not so simple to put a stack here and say these are infer the properties of these stars in terms of, for example, mass or age. No, but also we have the blue loops. So after the red supergiant phase, some of these stars can travel back to the blue and can be in the location where the OB stars are. So it's important to also learn about these blue loops that will depend very much on the mass or rate during the red supergiant phase, among other things like core overshooting and other physics. And also, as Hugh nicely showed us a few years ago, more than 70% of all massive stars will be interacting with companions. So the percentage of massive stars in binary and multiple systems is very large now. And in particular, 30% of them will interact during the main sequence. And as Selma, the mean told us, the percentage of mergers will be also quite, well, it's 10%. No? So this needs to be taken into account when interpreting our observational data, no? Because it's not the same, the tracks, the evolutionary tracks followed by a single stars or by a binary system. No? So again, this is making things more complicated here. And this is why for a given point in this diagram, so at the end, a point in this diagram is a star with a spectral type and luminosity class, we have to consider many stars to kind of have a correct range of rotational velocities and different potential properties of binarity and winds and everything. No? So this is why it's important to get as many data as possible. So in the IACOB project, I'm concentrated in the OB star domain. This is basically a question of analysis techniques that are very similar in all this domain. It's not the same as when you go to the red supergiant, that is the other phase where you find many stars. The models are different, so I decided to concentrate on the OB stars. So this first set, the observations, this is a very important pillar of the IACOB project, not only because it's needed for what I wanted to do, for what we want to do, it's also because I think it's very important to leave this legacy product for the future, no? Because this will survive. Models may change, but the observation will be there forever. So I'm trying to get as many observations as possible and to compile everything together, so then people can use them without the need to go to a telescope. So on one side, where I'm using different telescopes here in the Canaries, this is a small and medium-sized telescope. So this is allowing me to get a lot of data because it's easier to get time. And it's great when you have telescope like, for example, Mercator, that is working so nicely that allows you to really go from the telescope to the analysis part. So this is great. So on one side, I have a single snapshot and multi-epoch and time series spectroscopy to have spectroscopic parameters, surface abundances, to detect and study spectroscopy binaries, and then to also investigate spectroscopy variability. But as I will show you, I'm also benefiting from Gaia for the parallaxes and proper motions. And then from UV spectroscopy, there are no missions now to get really good data on UV spectroscopy for galactic stars, but we got Fuse and IUE and Hubble, and we have good data for many of them. And also thanks to TESS, this was not planned at the beginning, but this great. TESS is great, as you probably have heard or you know from your studies. No? So all this I'm also incorporated to the study in the IACOB project. In terms of ground-based spectroscopy, probably you've heard about the IACOB spectroscopic database. So just to say that the last observing run was in December, and after 12 years, I have almost 10,000 spectra of 10,000 galactic OB stars. These are bright stars up to magnitude 9 or so, and in the northern hemisphere. And also benefiting from the Sun telescope and Stella, I could obtain time series for a selected sample of stars with higher currents and longer time span. So this will be very important to complement what TESS is obtaining, and Kepler and K2 was obtaining from space, no, in terms of spectroscopy. Just in case you want to have a look, this is the renovated, renewed interface of the IACOB spectroscopic database. So even not all the spectra are now public. I put there all the stars for which I have a spectra. So in case you want to have a look to your and search your favorite star and there are spectra there, contact me and we can talk about sharing this data. The only thing is that for the moment I'm keeping some of the spectra for the students here, the PhD students, and the things we want to do. But if it's important for you, I will be happy to share with you specific spectra. And then we are also complementing this with FEROS archive spectroscopy, because we are concentrated in IACOB. Initially, we were concentrated in the northern hemisphere, but FEROS is very similar to Hermes and FIES. So we decided to also go to the FEROS archive and download all the spectra of O and B type stars. And also we will have somewhere during this year, the WIF spectrograph will be starting a survey of 5 years in the Herschel telescope. And this will be obtaining 5,000 resolution spectra of many stars. So this is a multi-object spectrograph. And there are like 10,000 fibers. So there's one of the surveys that is called SIP, that will be covering the northern galactic plane, and there will be many O1b type stars there. So just to show you where or the regions that will be covered by the different surveys. So here I put Orion, that is kind of 0.4 more or less kiloparsec. And then IACOB will be covering the northern hemisphere up to more or less 2 kiloparsec, and there will be around 1,000 stars. But then WIF will allow us to go up to 9 kiloparsecs, and then this will allow us to increase the statistics of the number of observations we have for 10,000 OB stars. So it's going to be great. The quality is not as good as IACOB, but then it's a compromise between number of objects and then quality. So I think 5,000 is a bit at the limit, but there will be interesting things to be done there. And there also is not here, but there is one survey with Formos that is planned, that is led by Nick Wright, that will be observing also in 5,000 resolution stars in the southern part of the galactic disk. So this is just to show you what will be the impact of WIF. So in red is IACOB stars that are already a lot, but then in blue is these are candidates, because many of them have been selected from photometry. So we will have to confirm if they are OB stars or no, but yeah, we are talking about now the candidates is like 40,000, so probably 10,000 will be good stars for us. Okay, so with this spectroscopy, we can do quantitative spectroscopy, and even from the single snapshot spectra, we can obtain the radial velocity, line broadening parameters, spectroscopic parameters, and surface abundances. And then for those stars that are SB2 system, we can also detect them. So we can already have some information about spectroscopic binaries. This is an example of I'm not going to enter into the details of the analysis, or even I'm going to show from now on some results. I'm not going to explain all the details, but from the people that will be quoted here, if you want, you can invite them to give talks, seminars there, and I will be happy. I'm sure they will be happy to tell you more about the details. So the first important results obtained by the IACOB project was obtained in the PhD thesis of Gonzalo Holgado, and he was doing the spectroscopic and physical characterization of the galactic O-type stars targeted by the IACOB and the OWN surveys. So OWN is a similar survey as IACOB, but concentrated only in O-type stars and in the south. This is led by Rodolfo Barba. So we are talking about 4 more than 400 galactic O stars. This is almost 70% of all known galactic O-type stars, and almost 3,000 spectra. So multi-epoch, why? Because we want to also identify the spectroscopic binaries and also to investigate the variability. No? So with this, Gonzalo was able to see that 40% were SB1 and 27% were SB2. So this is very similar to what other surveys have been obtaining in the last year. So the percentage of spectroscopic binaries in the O-star domain is around 40, well, between 40, 60, depending on the studies. Then he obtained spectroscopic parameters plus helium abundances for those likely single and SB1 stars, and these are the results put it in the kill and the spectroscopic HR diagram. So this is increasing like mad, the statistics, and this is very good because as you will see, increasing the statistics is allowing us to do things that we were not able to do before. So for example, just for comparison, this is the density map of stars analyzed by Gonzalo, and the previous similar work was done in 2015 by Fabrice Martin. And it's a great study, but you see what is the importance of increasing the statistics. So now we have many more stars there. So here we are covering more, a larger range in rotational velocities, for example. And then, yeah, we are also detecting the binaries here. So I'm starting to be able to do things like this. So we can really extract information from empirical tracks, either considering the models, but the models are model dependent, or at some point, thanks to Gaia, we will have spectroscopic masses. So we will be able to do the empirical tracks with the spectroscopic masses, and this will be great. Then also we are doing things like studies in details. This is obtaining the spectral type, luminosity, class, temperature, gravity calibrations. That is something that is not new, is known from a long time ago, but now what we are doing is to have a larger sample. We are considering those stars that are standards for spectral classification, and then we have a homogeneous analysis. We identify the binaries, so it's kind of improving a bit things. And as you see, compared with the calibration by Fabrice, they are not so different, but we begin to have not only the tendency, but also the scatter that is important. So for a given spectral type and luminosity class, you have a scatter in gravities and temperature. And this is important to be known by the people doing population synthesis. That it's not a value, it's a range of values to be considered. And then we are also going further in studies like it's known from a long time ago that we were not detecting O-type stars close to the thumbs. But always was like, okay, but it's because your statistic is low, the number of stars is low, or maybe you are not going for the fine targets. So here we are going for the young clusters, the faint targets, and still we don't find any O-type stars close to the thumbs. It's true that this can be a problem with the models we are using for modeling the stars, but maybe this is telling us something different. So what I learned in this study from the collaboration with the people in Geneva is that the way they are considering the accretion rate during the star formation process is because they need to reach this star here. But what happened following the things that have been speculated in the last years, if these stars here, up here, are just binary products, and these are the results of evolution of this star, and then at some point I'm traveling here. So then you don't need to have these mass accretion rates to reach this part. And then maybe what happened, if you move down your accretion rate, then the star is evolving through this, not the thumbs, but this will be kind of similar to what is considered in the low mass star, the stellar backline. So this is still speculation, but for the moment with these statistics, is a possible explanation. No? So hopefully with more stars or with surveys like WIF, we will be able to find stars here or not. But I think this is something interesting to put on the table. Since we are also obtaining rotational velocities in an homogeneous way, and the quality of the data is very good because the resolution is larger than 20,000, we can not only obtain this is something that is known since long time ago, but we are recovering the vicinity distribution of the O-type stars, but now we can also divide the samples in different parts of the diagram, different masses and different evolutionary status. So for example, we can learn here that the tail of fast rotating O-type stars is mainly concentrated here. So it's not that all O-type stars are rotating so fast, because in this part, we don't have many stars with high rotational velocities. So this is important because in many cases, we are using evolutionary models of 40% the critical rotational velocity because there were all these stars here, but up here, maybe this is not what we need to use, no? And also we are obtaining abundances, and we can connect the rotational velocity with the abundances, and this is connected with this empirical test of our theories or models of rotational mixing in massive stars. So you see here that we are increasing the statistics, and then here we can also separate the binaries from the likely single star. So I'm not going to enter into details. If you want to know more, as I say, you can invite Gonzalo for another seminar. But I wanted to show more or less where we are. And then the next step will be to obtain the CNO abundances. Then what is also the next step? Now with Abel de Burgos, that is my new PhD student, we are jumping now to the B supergiant domain. So these are the descendants of the stars. And what is very important is that, as you see, these are the blue dots are the models, and the steps are, if I remember correctly, is like 0.1 megayears. So you see that after leaving the main sequence, the stars are jumping very quickly to the red supergiant phase. So this is this terminal age main sequence. The width of the main sequence is dependent on things like rotation or core overshooting. So this can move. But the point here is, what the hell are doing all these B supergiants here? They shouldn't be there. And this is something that is known since long time ago, but we've tried many times, and we still don't understand what is happening with this star. So it could be that the main sequence has to be enlarged up to here, modifying the core overshooting, or maybe these are stars that are in the blue loop. So the idea is to use a large sample of B supergiants, including also Gaia astrometry and test variability, and the detection of spectroscopic binary to try to understand what is going in there, and obtain the spectroscopic parameters and the surface abundances. So this is where we are now. So you see here, blue is the O stars, and then this is the B giants and dwarfs, and this is the B supergiant domain here. So we are 140 stars analyzed, and we can reach easily 400 stars. So let's see. But you see that here we are already obtaining interesting things, combining the O star and the B supergiant domain. And it's interesting, we just discovered this week that now the number of fast rotating O star, that is 25%, that is more or less, as you will see later, what is predicted from the binary models. Now with these statistics, we found that the percentage of B supergiants with fast rotation is 25%. So this is very interesting. Keep track on what will happen in the next months. Okay, once you have the parameters, then to really characterize the stars, you need to go to the UV for the stellar wind parameters, Maxwell rate and terminal velocities. And if you want to have the fundamental parameters, you need to have parallaxes. You need distances and photometry for distinction. No? So this Gaia rate is helping us a lot. And this slide here is just to summarize how we have been improving in the last year. So this is the stars in Gonzalo sample. This is only O-type stars. So you see that from Tycho, this is the error, the relative error in parallax. This is 10%. So in Tycho, we didn't have data for many stars, and then any of them was better than 10%. With TGAS, we were increasing here a bit the quality, but still, or the accuracy of the data, but still. In year 2, we already begin to have some data with parallaxes. And then with year 3, we are really improving a lot. So let's see, I think next step will be smaller, but we are now like from 450 stars, we have that the uncertainties are greater than 10% for 85%. So this is already something to start working with. And here you see how the stars are located. So these are mainly the stars that we are investigating, located around 2 kiloparsec, 3 maybe. And you begin to see all the important associations here. So let's see what happened when we will now combine all the Gaia data with the spectroscopy data. But Gaia is also providing proper motions. So for example, we can start to concentrate in specific regions, and apart from the spectroscopic parameters, we can confirm the cluster membership using parallax and proper motion, and the total proper motion. You see here that this is the main, this is a pair of V1, and it's OP, A, and red supergiants. And you see that most of them are here, but some of them are outside. So some of them are runaways, or maybe they are not cluster members. And with this, you can incorporate new or extra important information that has some impact in the way you interpret your results, no? Because it's not the same if you know that this star has some properties and is a runaway or not. The way you connect this runaway status with the VSNI, with the probable binary nature, this is also important, no? Or maybe you are investigating this as a cluster and some of them are not in the cluster. So this is also things that we are doing. And then related to Gaia, the last thing I wanted to say is that when you go to Gaia webpage, it's like, we are going to obtain radial velocity, stellar parameters, surface abundances for millions and millions of stars. Okay, this is for cool stars. For massive stars, this is not true, because this is the Gaia IvS region. So this is the spectra that we are going to have with Gaia. This is really good, and there is nothing apart from Bayesian lines. So to really reach the aims proposed by Gaia, by the Gaia mission for massive stars, we need to complement this with a ground-based spectroscopy. So in this sense, IACOB and IvS will be very valuable for this, because we will be able to fill all these tables of data from Gaia with information that won't be there even without this data. And now for the last part of my talk, I jump to the time domain. So if we begin to include the time series and multi-epoch, we can study spectroscopic binaries, detect and study spectroscopic binaries, and begin to study stellar variability phenomena. So for example, here I'm showing how is the variability of kappa Cas and Rigel in H alpha. So for those of you who are working on modeling winds, so what is the phase that you are going to consider for your model? So this is something that I think there's a very interesting connection between what we observe and the models. No? Again, this is not new. So many of these things is not new. It's new for many years, and there are many papers on this. But what is new here is that the number of stars for which we have this multi-epoch and time series is increasing. So I think having more stars in a given region to see if the properties, a given property is constant or there is some scatter is also interesting. No? And then the detection of spectroscopic binaries or other features like stellar oscillations and spots. No? Things like this. These are the typical profile variability in stars with spots or radial mode pulsator, or G mode non-radial pulsator, or P modes. No? So this is also interesting. And okay, so massive binaries. I don't need to go into many details here, but I wanted to show this summary of things that have been obtained by Hugh and other collaborators in the last decade. So between 35–75%, the fraction of spectroscopic binary multiple systems with at least one O-type stars. 90% is the observed multiplicity fraction of galactic O-type stars with close-by companions if we add to this spectroscopy high angular resolution information. And based on these results, then Hughes and Selma conclude that 70% of the massive stars will exchange mass with a companion at some point. And especially 25%, you remember this 25 before, interact during the main sequence, so during the O-star phase. And then 8% will be mergers. These are predictions by these models. And then Selma told us, or showed us, or proposed us that the fast rotator tail of massive O-type stars are probably a result of binary interaction. So if we combine these fast rotators, binary interaction, 25%, this is interesting with the other results that I showed before, this one. So this is the vicinity distribution of the O stars and B stars, 25, 25, interesting thing. Okay, how is the IACOB project contributing to this research line? This is difficult with all the interesting things you are doing there in Leuven, as well as other groups in the world. But we are doing our best to kind of complement what you are doing. So, for example, in the case of Gonzalo's, this was not the idea, because the idea was the spectroscopic and physical characterization, but we have as an extra the identification of spectroscopic binaries. So we have this, as I was telling you, 40%. Okay, this is in the similar. It's a similar value to what other surveys have obtained. No? But we are complementing this with the abundances, parameters, the vicinity distribution, and all these things. What are we doing here? I decided to go with Mercator and not, and go for the B supergiant domain, because then, okay, now we know more or less what is happening here, but what is happening here? These are just the descendants. So I will show you now some results on this. And also, we started to obtain data, multi-epoch data of the fast rotating O-type stars to see, okay, if these are binary products and maybe mergers, what is the binary status of all these samples? And now we have also started with this, the fast rotating B supergiant. So these are 4 papers that are in different stages, and I think will be providing interesting results to complement other works. So this is kind of very preliminary, but I wanted to show already. So we have 47 galactic O-type stars with vicinity larger than 200. So this is the region where Selma proposed that are like the mass gainers and the mergers. And there are 54 known stars, and we have multi-epoch data for 47 of them. And then we are combining this with identification of runaways. Simon is helping us with the eclipsing binaries identified by TESS. And then we are also searching for cross-by companions, and we will be obtaining parameters and abundances. And this is the results. So you see here how is the radial velocity, the peak-to-peak amplitude of radial velocity. And here there is a very important thing. As you go to stars rotating faster, and taking into account that, as I will show in a minute, that all these stars are also pulsating, it's very important to separate the variability due to binaries and to pulsating stars. So this effect on the variability of the profile due to pulsation, when you have a broad profile, is making that maybe the radial velocity amplitude of variability that you derive is 50 kilometers per second. But this is not telling you that this is necessarily a spectroscopic binary. And this you see when you have high cadence multi-epoch observation, you see that it's not a binary, it's a pulsating star. So we are analyzing now in detail all these stars here, and we have detected like 12 SB1s plus 1 is not sure if it's SB1, and then 6 SB2 LPV. Still, these are kind of, we are still not sure. We need more data to really say it's a binary SB2 system or a pulsating star. So this is telling us that it will be between 25 and 40. At some point, we will have strong results to compare with the percentage of binary in this other range. And then I would expect some difference between here and here if here we have mergers and mass gainers. But let's see. So still, this is something we will obtain in the next months. When we jump to the B supergiant domain, so here is during more than several years, I think some of them is more than 10 years, different campaigns with NOT and Mercator. So Hans, you see that what we are doing there is useful, despite papers are still not there, but this was necessary. And also complementing with high cadence spectroscopy with some. So this means every half an hour or 5 minutes during 1 week obtaining data to really say this is a binary or is a pulsing star. And also we are identify the runaways, binaries, and all these. So with this is what we obtain. So this is the percentage of stars with a given quantity in or a given value in the radial velocity, the amplitude of variability, depending on the what you consider that is the threshold between being a binary or pulsating star. This will be the percentage. So this was obtained similar for the study of O stars and B stars and B supergiants in BFTS, but now we have data to be able to better constrain this threshold. No? And as you say, this is 85,000 resolution. So you will say, well, my accuracy is 1 kilometer per second. So the number of binaries here is because these are not fast rotating stars. These are relatively narrow stars. So my percentage is 95%. Or well, this depends on other sources of variability. So then here we have to take into account pulsations, and this you know very well there in Leuven. So this is, for example, we are talking about this part. So we are talking about the beta set and then this stochastic low frequency variability in the O stars and the supergiants. And you see these are the moments of the line. This is radial velocity, and you see this is not a binary. This is pulsations, and in this case that is kappa cas. This is the way the profile is varying, and even is 20 kilometers per second is not a binary. So then everything that is below 20 kilometers per second, we cannot say that is a binary in the B supergiant and also in the O-star domain. So what I did is, you see here, this is the same. This depends on the position of the star in the diagram, because the pulsations are different depending on the physical properties of the star. So for example, in the O giants, the variability is the periods are very short and then the amplitude is smaller. When you go to the OB supergiant, it's increasing and the period is getting larger. And when you go to the late B supergiant, the amplitude is smaller again, and then your periodicity is larger. So it's very important to kind of also combine your multi-epoch observation with this type of data to really say it's a binary of no or not. No? So here what I show is these are the stars that I analyzed. The black symbols are the confirmed binaries by eye, and then the rest are stars that are pulsating. So if you project this and this in this direction and this direction, the radial velocity, you see that all these stars here are pulsating stars, not necessarily binaries, maybe binaries, but we cannot, it's hidden within the variability due to pulsation. So this is affecting a lot, or this is helping to constrain the percentage of binaries in the B supergiant domain. And this warns us that we have to review again the statistics in this part, now that we know better what is the typical variability of spectroscopy, the spectroscopy variability due to pulsation. So then we reach this 10-15% of OB supergiant in binaries. This is a lower limit, but I think it's not going to change very much. So then it's interesting to compare this with the 40% in the O supergiant domain. Things to keep going and obtain results. Finally, obviously, I've been talking about the stellar variability. Stellar variability in spectroscopy is great, but it's very difficult to get the proper data to investigate pulsations in all stars in general, but especially in massive stars, because the periods that maybe on the beta cepheids that are shorter. For all stars and B supergiants, you need longer term observation and really high currents. So then TESS came here, was not the original idea, but the asteroseismic community is benefiting very much and is really squeezing what TESS is providing for study asteroseismology. So these are some examples of OB stars with test data. This is from the paper Simon published last year, 2 years ago. I think it was last year. So you see how great is the data that we have and how different is the variability depending on the properties of the star. No? So again, TESS is giving us the variability, but it's not telling us what this star is. So we need to complement this with ground-based spectroscopy. And in this sense, IACOB and IvS are going to be very useful. And we have, together with Dominic, or led by Dominic, we have submitted a proposal for high currents observation with TESS. And we are not proposing candidates. We know that these are OB stars. So we are going for the good ones, let's say. So I'm sure Simon has already told you about his work, so I don't want to say many things, many details here, but just to show and to highlight and stress how important is this type of work, and especially how important is to combine all this information from the periodograms obtained by TESS with the location of the stars in the HR diagram, and especially if we also have information about the possible binarity, rotational velocity, and all this, no? Because then we can separate variability that could be due to rotational modulation, that maybe the wind has created some macrostructure that are rotating and is affecting the light curve, from really variability due to pulsation. No? So I think this is a very promising line of research. It's very time consuming. But I think Simon is doing a great work there. This was only with data from sectors 1 to 13. So this is southern hemisphere stars. And you can imagine what will happen when we will combine this with all the data that I showed you before. No? So we can follow with this. So Simon, you have a potential postdoc if you want to come here at some point, and if we get funding. And then apart from this connection between stellar parameters and variability, we can also combine this with spectroscopic variability. For example, with H-alpha variability, or with when we combine spectroscopy and photometry, we are kind of seeing different things in the variability of the stars, no? And especially what will be very interesting, I haven't put it here, but we are also obtaining simultaneous spectroscopy to test. So this is what I was doing during this last December run, and it's very interesting what we see, because sometimes things are not changing in the same way, and this is giving information about the physics of what is happening there. So at some point we will combine, for a large sample of stars, photometric variability, for some of them spectroscopic variability, and then we will have a complete characterization of the properties of the stars. So I think we will be able to do very interesting things in the next years. And try to answer to questions of what is producing this variability. So is this coherent heat-driven G modes? Is this internal gravity waves? If it's these internal gravity waves, where are these internal gravity waves originated? Is in the core? Is in the surface convection zone? And what is the connection of this variability with this macroturbulent broadening? So here I put some works that we've done in the last year, and there will be more, because this is just a starting point for this research line. So as a summary here, well, basically just to highlight again what is the objective of the IACOB project, that is obtain this statistically significant empirical overview of the physical properties of galactic stars, spectroscopic and fundamental parameters, abundances, spectroscopic and photometric variability, kinematical and environmental information. And thanks to all this combination of all these observations, and the expertise of different people in different places, I think there are very interesting things that the observers will provide to the modelers in the next years. So combined with the developments you are doing the modelers, I think it's a good time for massive stars. And then the other thing that I think everybody is now starting to go in this direction, we are talking about 10,000 stars. We have to go at some point to use of big data and deep learning analysis techniques. And here we are also developing and starting to think about this possibility. Thank you very much for your attention, and I will be happy to answer your questions or discuss with you.
Sergio. Sorry, Joris, go ahead.
Thank you. It was a very nice talk. Very large variety of topics actually. So very nice. So okay, if there are questions, please post your name, and I will, as usual, go to the younger ones first. And the youngest one at the moment is Tomer.
At the moment. Thank you very much for the talk. It was really interesting. I have a few questions, but I'll start with one to not dominate. About the post-interaction binaries. You said how difficult it is to reach amplitudes, like to detect binarity when the radial velocity amplitudes are lower than 20 or so, or 30, depending on the star. But the problem is those same people, Selma and Ug, are telling us also that these post-interaction binaries would tend to have amplitudes of this order of magnitude because they have companions that are lower masses and so on. So my question is, how can we advance, in your opinion, on this, and how can we find those binaries?
Yeah, this I think that the first thing, and this is what I wanted to highlight, and there is a paper that will appear soon with all this, is that be careful with when you provide the percentage of binaries, because maybe, so you need to go more in detail on this, because it's not, if not, you can go to 80% and then your results or your conclusion can be spurious, no? So what I found is that in the paper, in the appendix, I have a proposal for this. So I've been able to do this because I have access to all these telescopes, and it's easier to get data. But then if you at some point, the magnitude of a star does not allow you to do all these high currents observations. So for example, the usual strategies, observational strategies to detect binaries is still okay. So like maybe 20, 25 observations distributed in different kind of slots, like weeks, months, years, to be sure about the different periods. But then what I suggest is, and this is why I wanted to have this paper to convince the panels, that we need to go for each one of them. Would be great to have, like, during 3 days, 1 hour observations, or a cadence of 1 hour, because in this way, what you obtain is the variability that you expect from the pulsation for this specific star, and then you compare this with the other data, and then if it's below, it's going to be very difficult. But at least if it's at the limit, and then you say, imagine that you go for a star in which you see that the variability due to pulsation is 10 kilometers per second, and then you see that your long-term variability is 20. So it's like, so this one is more likely a binary, spectroscopic binary. But then if you see that in a few days is 30 kilometers per second, it's like, I cannot say anything. So this is the way to slowly but surely try to increase our statistics a bit up, to really reach the number of spectroscopy binaries. I think this is the way to go, because if not, the other way would be to with a periodogram, separate the period of the binary from the pulsation. But this requires months of observations in high currents. So this is going to be impossible. So this is my proposal. Maybe other people have other ideas, but at least the problem is there, and some guidelines for future consideration.
Okay, thank you.
Okay, then we have Simon, please.
Hi, Sergio. Thank you for an interesting talk. Many interesting future prospects for sure. I had a question about when you were talking about the birthline and Gonzalo sample showing a dearth of Zam star, and then you also showed a little plot with the different birthlines. Could you explain maybe a bit more about different physics that went in those birth lines? And
yeah, so the point here is that when you have the premium sequence star, they are moving from the starting point, following the Hayashi tracks, or the Hayashi-Hennig tracks. And then at some point, the stars are accreting, and at some point, if the material is not there anymore, then the star have a given mass, and then is traveling to the thumbs, is contracting until you have hydrogen burning. In low mass star, the time scale of this premium sequence phase is so long that normally you accrete all the material before, and this is why you see all the YSOs and all this. No, when you go to the massive star domain, at some point you have since the contraction is faster, and then you can reach the thumbs while, or is one possibility, while you are still accreting. So then you reach the thumb position and you are still accreting. But also the star, since it's already burning hydrogen, is already evolving. So then you have one direction towards lower temperature, effective temperature, and then one direction that is, so this is evolution, this is accretion. So then one suggestion was like, okay, what happened is that you don't see stars close to the suns because you still have accreting material, so you cannot see the star. The star is in the cocoon. But if you go to fainter targets, maybe you see those stars. So still this is some possibility. But then the other possibility is that if instead of saying that you are still accreting, if you are accreting faster, because this is a free parameter they are considering, the accretion rate. And this, they put it so high because they say, since we know that there are 100 solar mass stars, we need to reach this position with an accretion rate that is faster than the evolution. So this is why they needed to put it so high. But then if finally this is the stellar birth line, then you don't need to have such a high accretion rate. So it's very important, and I think we need to consider this for the future in the next year. We need to try to see if the high mass stars are all of them products, binary products, or not, because this is going to modify all the constraint for star formation in massive star, for the accretion rate and everything.
Interesting, thank you. Yeah.
Okay, now we have Garrett.
Hello, hi. Thank you for the very interesting talk. I just had a question concerning the scatter on the RV scatter with the pulsations that you found in the OMP supergiants. I was just wondering whether you had any indication if this changes for stars on the main sequence, so for O and B stars for the main sequence.
You mean the usual radial velocity that you detect
Yes.
in all the stars? Okay. I have some ideas. So, for example, what is happening there is that the O stars close to the suns are not supposed to pulsate. Maybe they have stochastic low frequency due to internal gravity waves. This you can talk with Dominic. But in principle, they are not expected to have coherent P modes. When you start to evolve, then your star is getting larger, and then at some point you enter in the beta Cephate domain for massive star. So then you begin to see a larger amplitude of variability. And then when you move further, at some point you have also the G modes. And so since the star is also larger, so your amplitude is larger, and then your periods are longer. So then there is kind of a gradient. For the O dwarfs, I would say that the typical variability is of the order of a few kilometers per second. And then in the giants, more above is around 5 to 10, and then you go to 20. So this for the O stars. When you go down in mass to the B star domain, then you begin to enter into the beta Cephate domain close to the suns. So then maybe we are increasing again this effect. And then if you go down in mass, you begin to enter into the hybrid and the SPB. So I think, but you have people there to ask this question that they know better. So I think not from spectroscopy, maybe not from directly from spectroscopy, but I think, and this is the other thing I wanted to do. How is the correlation between the photometric variability and spectroscopy variability? This is going to be great because then we have a photometric variability. So if we find a correlation, it's like, okay, what do you expect for this star from test? Given the amplitude of photometric variability, this is what you expect from spectroscopy variability. So I would say that when you go to the B to Rs, you begin to enter again in a dangerous domain because there the variability, and also you have the spots and all these things. So maybe it's not as large as 20, 25, 30 kilometers per second as in the B supergiants, because this is also because the stars are very extended. But one has to be careful there. So
okay, great, thank you.
Okay, then we have Pablo.
Hi, Simon. I wanted to ask a question again regarding the birth line. So if you have stars that are obscured and you don't see them because of that near sun, radiation still has to come out somehow. So do you expect it to be reprocessed and you should be able to observe them in the infrared?
Okay, this is one of the lines that we plan to follow, or at least suggest, so we cannot do everything. So, but it's one suggestion there. So try to do a similar, so go to the infrared, because one side you have like this reprocessed emission, as you say, and then you are able to go deeper in the cocoon. But this will require, so there are not surveys of OB candidates in the infrared, extracted from the infrared. So this is something maybe some young student can concentrate on that. But for that you will need first the candidates, then go and obtain the infrared spectroscopic observation, and then obtain the parameters. And then the infrared is not as good as the optical to get the parameters. But this is one possibility, and we need to go in this direction at some point. And then the second option, and this is kind of related to what you say, not in the infrared, but you have O stars within the cocoon, because the masses are of the O stars. So then you have ionizing flux. So you are obtaining this, what is called the ultra-compact H2 regions. So then if we now can revisit the percentage of ultra-compact H2 regions from what we expect in terms of the number of O stars and the number of ultra-compact H2 regions, if we find that we are missing ultra-compact H2 regions, this is also going in the same direction as I was saying, that we don't reach the thumbs. Because if the evolution is following the stellar birth line, you are not reaching such a high temperature, and your ionization depends on, so at some point, if it's below 30,000, you don't have H2 region. So this will be another possibility to try to different approaches to see if there are O stars embedded in the cocoon or not.
Yeah, thank you.
Okay, then we go to John.
Oh, great overview, Sergio. Thanks. Actually, I was very intrigued by your new B supergiant results, I must say. They were, I hadn't seen them before. So I was actually wondering, so I guess, I mean, you find a population of fast rotating B supergiants now, right? Do you also know, I didn't see from the HR diagrams, or I didn't have time. Do you also have mass estimates of these stars? Do you know roughly where they are? Are they like, you know, on the lower end or on the upper end, or?
These are, so I don't have it in the HR diagram. I have it for the moment in the spectroscopic HR diagram. Yeah. But this, what I show there, so I'm going to go again here. Where is it? So it's this one here. So
right.
This, for the moment, these are only the early B supergiants.
Okay.
So the blue is the all stars. So this is B0, B1, B2 more or less. We have more, but still under the process of analysis. So this part is 15,000 more or less here.
15,000 roughly, yeah, 15,000. And are they very small enough? Do you have radius estimates?
Not yet, but so this was obtained this week. So I'm still processing this. And then the thing is that the other thing that we discovered is that Gaia DR3 data seems to be good enough to try to go for luminosities, and then we will have radius. But so we will do this at some point.
Yeah, that would be very interesting to see.
Yeah.
With respect to particularly, I think how close they would be to, say, the Eddington limit and stuff like that. If they're really.
There are some of them that the Eddington limit is more or less here in this up here. So some of them, but this is more or less what. So the stars that are close to the Eddington limit are those that are classified as luminosity class 1A plus. So some of them are already known, these hypergiants.
Yeah.
But what is happening is that since we are increasing the statistics, we are discovering a few more. So most of them will be the ones that have been studied already.
Yeah.
But there will be a few more. And then we will also have that, I think this is also important, the variability of H alpha. That is...
this is also a little bit. I saw that from the end. I mean, this is of course very, very interesting to see. What do you see any? Have you? I don't know if you have been analyzed. Do you see any systematic trends, or does it look stochastic?
For what? For the
H alpha variability, say.
This is something that this is mad. So it's really. I think at the end you have a combination of these micro clamping plus macrostructures with rotational modulation, and also if you have some binary. So no, there's no systematic. I haven't done it really carefully, but from what I see, so it's like, look, this is B1A. And then you see no variability, and then you go to the next one, and it's no. And some of them are in absorption, some of them are in emission. So
it would be very interesting to see if you find any systematic trends also with respect to, I don't know, how close you are to the Eddington limit in some sense. I mean, if what we're trying to model currently, with radiation-dominated envelopes, that basically causing a lot of structures, right? At least qualitatively, I would expect that you would see some sort of trend with lower, perhaps, variability and lower characterizations the further away you go from so to say, the Eddington.
Okay, so I would say that at some point, because now Abel has been concentrated in the first spectroscopic analysis, but then to know the sample and everything and what is missing in terms of observation, then now we have the stars in the diagram. We will begin to start analyzing the multi-epoch, and then selecting stars for follow-up multi-epoch observation. So probably during this year, I will tell him to go in this direction, and then we will tell you as soon as we will have some result. We will tell you.
Perfect. Yeah. It's really, those are looking forward to seeing it. A lot of nice stuff there. Okay, thanks.
Thank you.
Good. Andrew, you also had a question?
Yes, thank you. Well, time for questions from audience. Hi, Sergio.
Hello.
Thanks a lot for the nice presentation. I actually have two very short comments and one question. So comment number one, so you mentioned that there are no surveys looking at high mass stars in the infrared. That's incorrect, as the SS5 kicked off, and there is a large program on young stars in the entire mass regime with multi-epoch near infrared observations.
Good to know. That's right. I didn't know. Good to know.
Second comment is, so when you mentioned looking for possible correlations between the photometric signal and spectroscopic signal, you mentioned amplitude. So I would be careful there at least, because TAS has a huge pixel size, which means lots of contamination, and contamination means amplitude dilution, and predicting that dilution factor is not so easy. So
yeah, I agree that we have to be very careful with the interpretation of test results, but since we have so many stars, because now it's not that we need high currents, so we can go to all the, at some point if we have 5,000 OB stars, then we can extract, since we have the apertures, those that are less contaminated. So obviously there will be a huge scatter, and sometimes you see that you see an eclipsing binary and you say, why you have an eclipsing binary? Is because it's a companion. But at least since we have large statistics and knowing that, I think we will be able to, if we have like 30 stars without contamination and good data, I think we can reach this at some point, let's say, no?
Okay, and so my question was a follow-up on Tomer's question, so about delta RV essentially. Yes, so you mentioned that you can induce the RV variability of some tens of kilometers per second by intrinsic variability as well as by binarity. So I agree, especially when you have, you know, like broad lines. Yes? So perturbing that line a little bit can trigger some RV variability. But RV is an integral value of the line profile. So why not, instead of, you know, starting doing more observations with a higher cadence, why not studying the line profile itself in greater detail? Because binarity would essentially imply a global shift of the profile, while intrinsic variability of the star will result in some skewness of the profile. And by doing bisector study or kind of thing, you might be able to distinguish between.
Yes, but there is a caveat there, that in the B supergiants you are going to have always pulsations. So even if it's a binary, you will have pulsations. So you are combining both. So you will always have asymmetries. So even if you go to the profile, and I've, as you saw, I put the 0 moment, first moment, second moment, third moment. But the problem is that you have both things. So it's not that you have either pulsation or binarity. Is that you have always binarity, always pulsation, and then binarity. So you will have, you cannot use the thing that is a symmetric line moving, because maybe the star is pulsating plus moving. So it's not so, but obviously you are more expert on all this than me. So if you find a way to try to separate both, it will be great. But from what I've been kind of trying to find, it's not going to be so easy, because we are talking about, it's not the same as, for example, in the B dwarf domain where you don't have macroturbulent broadening. So here in all the stars, even if you go to very low vicinity, you have a huge macroturbulent broadening. So the profiles are not narrow. The profiles are triangular and quite, so you have this 60 kilometers per second of macroturbulent broadening. And as you see, this will be dancing. So it's we can talk more about this, and maybe you have ideas, and I have data for you to try to find something. And if you find a way, I think this will be very valuable. But I have the impression that it's not going to be so obvious.
Okay, thank you.
Okay, then last but not least, Hans.
Yeah. So thank you for a nice talk. It's always, of course, good to see nice results of Hermes. But I have a question on the luminosities, because you say, okay, Gaia gives you the luminosities, but you still have the reddening. And is there an issue with the reddening to determine? And do you use diffuse interstellar bands for the reddening, or is that?
No, basically, for the all stars, I'm just taking the result from Jesus Maria Pellanid. So this is from set fitting using as many photometry as possible, and the extinction laws and everything. So it's not obtaining calibration of interstellar bands with reddening. It's obtaining the reddening itself with the fitting, since you have the parameters, you have the synthetic spectral energy distribution, so you can use your photometry to modify your synthetic to the observation to get the distinction. This is the way, and also so there is code that is using as free parameters the RV value and the extinction. This is the way we are doing that.
And did you look at the diffuse interstellar bands and how do they link with the reddening?
Yeah, I know that Jesus is going in this direction, and some proposals in Mercator goes going for start with high extinction, but I'm not the guy. I'm not the guy to answer this question. Okay. But if you are interested, I think for the O stars especially, Jesus is the one to ask.
Okay, thank you.
Okay, thank you very much. I don't think I see any other questions, so maybe I should ask Laurent now. Do we want to bombard further during a coffee break, or or what do we do?
I think we can stop for 5 minutes and go for coffee, and then come back after and talk, with Sergio.
Yeah. Okay, that's great. So we'll have a coffee break for 5 minutes, and then those who are interested to discuss further, they come back to this channel that will remain open.